Now, before I go any further, I want to start introducing tactics. And the reason for that is because it's worth learning tactics at the beginning when you are being introduced to the simple parts of Lean, just so that you can see how the simple parts map to tactics. Lean has two different modes. There's term mode, which is what we've been using, where things just have values and types. And then there's tactic mode, where Lean expects a certain tactic, which is basically some kind of meta-programming, but for theorem proving. And it's just different. So to go into tactic mode, you use the by keyword. So here's theorem T1. We're going to prove T1 using tactics. So instead of just having a lambda, we're going to say by. And the first thing about tactics, the first tactic that you want to know is the intro tactic. Intro does what a lambda abstraction does in term mode, but in tactic mode. So here we're going to say intro HP, and this will assume hypothesis P. You should be able to see, oops, I messed up, so let's call this tactic. So before we introduce something, the goal is P implies Q implies P. After we introduce HP, the goal turns into Q implies P. In other words, intro takes the left-hand side of an implication and puts it into a hypothesis. Now there's another hypothesis, which is Q, and we already know we can use an underscore for that. So we'll just hit underscore. Oops. And now we just need to show P, the goal, but we have HP. And here's where we might try to do HP. This doesn't work because we're still in tactic mode. Remember that once we said by, we entered into tactic mode. To get back out of tactic mode, or, well, to use an expression, a tactic that uses an expression, a term, to solve the goal is exact. There are a few of these, but exact uses an expression to solve the goal completely, and it fails if it can't. So the hypothesis that is given here must match, or the expression must match the goal exactly, precisely. Great, so we have two T1s. One is proving using basically term mode with functional programming, and the second one is using tactic mode. And the reason why Lean has these two kinds of methods is because Lean is fundamentally a functional programming language. But when you boil everything down, everything turns into functions, right? And you'll see that when we get to logic, especially with negation and sets, they're all defined as functions. But functions are a bit less readable than, or at least not, they don't look the same as a proof usually looks like in math. Tactic mode is meant to make functional programming look more like mathematical proofs. It's a lot more than that, but that's one of the things it does. So here you can see that, assume the hypothesis. Intro hypothesis is a lot more math-like than, fun HP of type P. So there's actually a very helpful variant of exact that looks up in the current scope identifiers that might solve the goal. And that's called exact question mark. And you can see that once I get rid of HP, suppose I didn't know HP existed, we can type exact question mark and hit Control dot to get the suggestion of exact HP. And Lean is finding this automatically for us. So this is very handy when you get to more advanced proofs where you might have a lot of things that you know, but you don't know exactly how to apply them. So moving on, we left off on P and Q. I'm going to go a little bit quicker to get to the first few problems as soon as possible. We have disjunction. It's worth looking at for sure. I'm going to prove this really quick just to show the tactic way of handling ORs. So we're going to prove the commutativity of P or Q. We can call that let's see, let's go down a little bit. Let's call this theorem. We'll actually start naming our theorems something sensible here. And we'll rewrite this to be a little bit different. It's a bit more straightforward here. We're going to have the parameters p and q. Oh, sorry, we already declared those as variables above. Let's get rid of some of this noise. So up here, when we declared p and q as a variable, we don't need to redeclare them in our theorem. We can just directly state p or q implies q or p. And we will do this two ways, of course, one with tactics and one without. In the first one, we know that if this has type function, we're going to have to give a function expression, or a lambda, and we can do that with fun. Now, personally, I like to do \LA for lambda, but don't worry if that scares you. You can use fun as well. And we're going to take a p or q as an argument, and we are going to return some kind of theorem. Tabs got messed up again. Fix that. Okay. And then in the tactic mode, we're going to do much the same thing, but with intro instead of taking a parameter as an argument. So right now, if you want to do it the way the book does it, the book uses this function called or.elim. Let's just look at that real quick. And this takes an or, and it basically takes a function for either case of the or that maps both of them to another type, C, and it just gives you back that C because it can do that in either case. So it kind of eliminates the or by handling both cases. This is the same as just doing a pattern match, okay? So we can, instead of using a built-in function, more generally speaking, you can pattern match on inductive types with the match keyword. In term mode, you would use match. We're going to match on a p or q with, and now we're going to need to give both cases. Lean is saying unexpected token here. A bit more helpful error message would be missing cases, and you'll see that in tactic mode you do get that helpful error message. But we'll just add the bar, and or has two cases, two constructors. For an inductive type, when you're pattern matching, it's always on inductive types, and you always have to give a constructor. A constructor is just a special kind of function that builds something. It must return an inductive type when it's done. So we have match p or q, and we'll just put, for now, let's see if we can kind of use Lean to help us figure out what to put here. I already know, but I want to see if we can figure it out on our own. And I'm just going to put sorry for the first case. And now if I match over this underscore, if I mouse over it, I don't really get much information, unfortunately. So we'll go back to this in a second because the tactic mode will be a bit more helpful. In tactic mode, instead of match, the keyword is cases. Is case or cases? I think it's cases. And we're going to match, we're going to do cases on P or Q. And already, without even typing anything else, you can see that our goal has changed. So now our goal is has multiplied. It's two goals now. And we have both cases, INL and INR. And that's probably a really good clue as to what we'll put in the term mode, in the exact mode up here for our match pattern. We'll just finish this off real quick though. When we have two cases, you can do this one of two ways. You could say with, and then we can give our alternatives, inner and INL. And these stands for injection right, injection left. Injection on or says that, you know, if you have, if you want to show P or Q from P, you can do that just by adding an or Q. You can always do that. So if you want to do this, you have to give a argument to the constructor, because the INR takes an argument, and I wish it would show me the function here. We can be explicit about it and say or.inr, and now we get a bit more information. This takes right injection to an or, it takes a B. So we're going to call this, if this is our left side, we're going to call this HP, I believe. Now let's just make sure that our HP actually has the right type, because this is slightly guesswork. Oh, we can't see it. Okay. Then we'll go down here for now and we'll say HQ. And now we are getting an invalid alternative name. Okay, so we're actually not allowed to use the name of the constructor here. That's a little bit weird. That's kind of just Lean. So we'll get rid of that. But we needed it to help us, figure out what INL was. And you know it's or.inl and or.inr because, of course, it's a constructor for the type or. So you know it's going to be under or. Okay, so we'll get rid of that. Get rid of that. And now let's make sure that we have the right types. Okay, now we can see the types up here, HQ of type P. Clearly that's wrong. I mixed up my left and rights. This is HP, this is HQ, and we'll just put them in order. Okay, now I have to show Q or P from HP, and I have to show, down here, I have to show Q or P from HQ. And we actually already know how to do that because or.inl, the pattern, the constructor that we're matching on, is the same constructor that we want to use. So we're going to say, in this case, it's probably going to be the left one, I mean the opposite one, so the right one. So we're going to give or.inr with HP. And now we get a bit of a weird, well, it's not that weird. It's actually a quite useful error message, unknown tactic. And we've forgotten that we're still in tactic mode. We've actually never left it because the by entered tactic mode. So we have to say exact here. Okay. And suppose we don't want to type that in on the second one, we can just hit exact question mark. And Lean here does give us a solution, but it's a little bit weird of a solution. It's saying basically you can use the right constructor again for or with applying symmetry. I don't care about that. I don't want that. That's just noise. We're going to change the right to left and then just use it directly, and we're done. So that's tactic mode. Now it's a bit extra work to do intro PRQ and then cases PRQ. There's an even shorter way to do this in tactic mode, which we'll get to in a second, that uses more built-in pattern matching, which is very useful to know, both just in general, but also to read code. A lot of Lean code is written with more inline pattern matching, which I'll get to. So, but let's finish this first. OrCom in the term mode, we had our function, our lambda. Let's put this on another line just to make it a bit more readable. It takes a PRQ of type PRQ. We could be explicit about that type with PRQ, like that. And we need to match with both cases. Well, we already know that the constructor for PRQ is going to be or.inl HP. We know this because we know down here that we got two cases, INL and INR. And even though these case names are somewhat arbitrary based on what tactic you're using here, these aren't the actual constructors. They do match the name of the constructor. So we can assume that this will be or.inl, and it is. We don't get any error messages. And we'll just copy and paste that again. Change this to Q, change this to R. And now we're set. Before we did that, I would hope that match would complain when we were up here. It's not complaining. I see. I've already declared OrCom. So OrCom is already declared in the standard library. So we're going to need to say my OrCom. Okay, and now match is complaining as I expected, and it's saying missing cases. And actually, if you comment this out, unfortunately, that we don't get the missing cases with two cases, and I'm not quite sure how to get that to show up. But anyways, if you have one case, it knows that the other case is not there. So we have INL, so it knows that INR is missing. So we'll add it, and then we need to prove this, and we're just going to use the same way. I'm just going to move this up just to avoid noise here. I'm going to just take this out, and we'll do this the shorter way below in a minute. Oops. Okay, and let's just get rid of the exact. We don't need exact because we're not in tactic mode. And we can give, we do need the or.inl for the constructor because we're in term mode. All right, that works. Perfect. But down here, I said I was going to do it a little bit of a different way. We're going to use much more of the tactic functionality here. And we're going to do that with, instead of intro, we're going to say our intro for, basically, if you look at our intro, it's the intro tactic with our cases to allow destructuring pattern matching, right? So this is pattern matching when you introduce a variable. So we're literally going to skip P or Q entirely, and we're going to use our good old fashioned, oh, actually, we don't get to use those. Those are for and. This is going to be parentheses, P, and then we're going to use the bar pattern for an inductive sum type. That's what this is called. When you can have one type or another type, that's a sum type for inductive types. And would be a product type. So when we do this, you can see that what happened in the goal state, we suddenly have two goals now, and they're named the exact same as they were before when we were doing the cases tactic. It's just that we've skipped some of that work, and it immediately shows up as two goals. And now we can't use the bar anymore, I don't think. We could use the case tactic. Actually, there's a case tactic that says case INL by sorry. That would work, and then we could do the same for INR. We don't even need to name the cases. We can do \dot to enter into the first case and try to solve it like that. So we could do two sorries here. A little bit less readable, but you need to know how to read it anyways when you look at other proofs. So this just means enter into a subcase without naming it or choosing it at the first subcase. Okay, and how do we go from there, right? Well, we can actually still just do, we don't have to do any more work here. We can just say exact and let Lean figure this out for us. And Lean is smart enough to know that even if you don't specify that you're going to be working on a case, sometimes it's smart enough to know that just to start solving cases when you have a goal that, when you have something that matches, a tactic that matches the one of the cases exactly, right? So in this case, exact can solve the first case entirely. And so Lean will let us use it, and we can just type in exact again and do the same thing, right? And again, we get that or symmetry, which we'll get rid of, replace with L. Okay, now this is a little bit less readable though. So I do like to either have the case or at least the dot syntax to be explicit about the fact that we're handling cases. Because, you know, reading exact twice in a row is a little bit weird. Exact is supposed to close the goal. So it makes it a little bit harder to read. Okay, so that's the com tactic. The or com done by tactics. Now, I want to get to a harder problem here. Now that we have discussed, you know, the two kind of ways of building and destructuring ands. By the way, this works to destructure ands just as well. Now that we have that, those tools should be enough to let us solve harder problems, right? So let's look at something a bit harder. Oh, we have to get to negation first. Okay, so negation is a little tricky. This is important to understand. Not P is actually defined to be P implies false. So like most things in Lean, that you might think of as not related to functional programming, they actually are defined just as functions in Lean. And that's again because Lean at its base is a functional programming language. So if not P is actually defined to be P implies false, it can lead to some weird cases that you need to be aware of. I'm going to go down here and show an example of that. So suppose that we have not P. So / not to type in not P, and suppose that we also have P. So we're going to show a contradiction from this. So we want to show false if we have both of these. This is called absurd in the standard library. So to do this, we have to give an example, we have to give a function expression for this implication, right? So we need to say, if we're doing it in term mode, lambda or fun, not P, and then we're going to take in a P, and we need to return some kind of contradiction, right? Well, how do we do that? It turns out that because of this definition, not P actually being defined to be P implies false, we can actually apply the not P, because it's a function, to P. And that looks kind of weird to a mathematician. I wouldn't know because I'm not one, but it does look kind of funny to me too. That looks like this. Apply not P to P to get false. And what we're going to do is, because it looks so weird, we're going to be a bit more explicit with our types. So one way of doing that is literally in the goal, to rewrite the goal itself, even though it's equivalent. If you know it's equivalent for sure, you can do this. We can say that P implies false. Okay, and that makes things a little bit clearer. But then we notice something funny, right? As soon as we do that, wait a minute, we actually have our goal like right here. And what that means is that you can do something cute here, which is currying. So we can say another way of doing this, which might not be the best idea for a beginner, but do it anyways. Not P goes to not P, right? Because now we're just returning the function P implies false directly. And if we know that this works, this is just the identity function, right? So we can just say ID here. That works too. And then when we to maximize this unreadability, we can change back our goal to confuse people, and we can say that not P implies false by ID. And this is the first example of where the Curry-Howard isomorphism becomes very interesting, right? We have a concept in math that is seemingly completely unrelated to functions, and yet as soon as you define this not P to be basically a proof by contradiction, as soon as you do that, you get this very cute definition of absurd, right? And that's really pretty. So we'll be seeing a lot more of these as we continue, but for now, let's just get into an actual problem as soon as possible. We have ways of defining if. You should read that. Basically, an if is very similar to an and. Auxiliary subgoals, that's what we talked about already too. And then classical logic is where you have access to the general proof by contradictions, not just the specific ones like not P. And so to access that, you would have to open classical or use decidable dot definitions, and we'll get to that. There are some proofs in logic, of course, that you can't solve without having access to things like absurd or EM, the general versions that say, like not P implies P. In other words, the double negation elimination. But I'm assuming you already probably understand the logic. The logic isn't that hard to understand. So we'll start right away with, we've already done some community stuff. We'll start with associativity. And this will be, associativity is kind of where you start getting to, if you're anything like me, parts of Lean where you'll get stuck and you won't have, you won't know how to make progress. And in the next episode, we will talk about, what kind of tools you have available to you when you are stuck and when you don't know how to make progress to start incrementally breaking down the problem.